Hello everyone, my name is Songrano. I'll be presenting the paper titled The Scene Language, Representing Scenes with Programs, Words, and Embeddings. This research, authored by researchers from Stanford University and UC Berkeley, has been accepted to the CVPR 2025 and was selected as a highlight paper. First, let's briefly touch upon how this paper, the scene language, distinguishes itself from many other generative AI papers. Typically, papers in generative AI, whether they are training for it or require training, tend to propose their own unique methodologies. They often present a novel model that focuses on how to generate an output directly from a given condition. This model often has an integrated or tightly coupled renderer. In contrast, this paper takes a different approach. Instead of introducing an entirely new end-to-end generative model, its core contribution lies in proposing a novel scene representation. The authors propose a system where an existing language model, indicated by the snowflake icon, is used without any fine-tuning to generate the scene representation. Once this representation is created, it can then be processed by various off-the-shelf renderers, essentially pre-existing and diverse rendering tools, to produce the final visual output. Therefore, the central question and the measure of success for this paper revolve around the effectiveness and flexibility of this proposed scene representation, rather than the novelty of generative model itself. Let's outline the key contributions of this paper. As highlighted on this slide, first, the authors propose a novel scene representation called scene language. Conceptually, this scene language is composed of three main components: programs, words, and embeddings. We'll delve into these components in more detail shortly. Second, they introduce a training-free method to infer the scene language. This method leverages the code generation capabilities of pre-trained language models to derive the scene language from either text or image inputs, all without requiring any fine-tuning of the language models themselves. Third, the paper details how this inferred scene language can be rendered into an image using a generic rendering modules. This means it's designed to be compatible with various existing graphics rendering techniques. Finally, through extensive experiments, the authors demonstrate their proposed scene language achieves great empirical results. It shows high flexibility by successfully integrating with different rendering modules, and exhibits superior performance on text and image prompt scene generation and editing text compared to existing methods. Now, let me briefly introduce the core concept of scene representation as proposed in this paper. The author starts by asking a fundamental question. What is important in representing a scene? Or, what characteristics should a good scene representation possess? Their answer is that a scene can be effectively described by three key components, which together form the scene language. First, we have programs, denoted as P. Programs specifically hierarchical and relational structure of entities within the scene. In this context, the individual properties of an entity are less important than how these entities are structured and relate to one another. For example, their spatial arrangement or grouping. Second, there are words, denoted as W. Words summarize the semantic class of each entity. For instance, if you imagine the word apple, everyone might picture a slightly different specific apple in terms of appearance, but they all belong to the broader semantic category of apple. This conceptual grouping is what words represent. Third, we have embeddings, denoted as Z. Embeddings capture the visual identity of each entity. This includes their actual appearance, shape, texture, and other visual details. So, according to the authors, any given scene S can be represented by the scene language, denoted as pi-S, which is composed of these three elements: program, words, and embeddings. As shown on the slide, this is formally expressed as pi-S being equivalent to the tuple WP set. Let's illustrate this with an example of 4x4 checkerboard. As shown on the slide, imagine this checkerboard. It's composed of a total 16 cubes, 8 black and 8 white. These individual cubes are the entities H that make up our scene. Now, let's break this down using the scene language components. The program, in this case, defines the arrangement of these cubes, how they are placed to form the checkerboard pattern. The actual appearance of each cube isn't the focus here. What matters is their relational structure and layout. You can see this representation abstractly by the cloud-like arrangement under program. The word corresponds to the semantic category, which is simply cube. All entities, regardless of their color, belong to this class. Finally, the embedding captures the specific visual attributes of each individual instance. On the slide, for simplicity, black and white are shown to represent the color of the cubes. However, it's important to note, as indicated by the clip text encoder arrow, that these are actually high-dimensional vectors. These vectors are obtained by passing description, the black cube and white cube, through a clip text encoder. So, the embeddings represent much rich visual information than just color. So the entire checkerboard scene pi-S is a combination of this program, defining by 4x4 grid the word cube, and the specific embeddings from the black and white cubes. Let's now delve into the entity function. A core concept of scene language is the assumption that all objects are hierarchically structured. While we might have simplified this in the earlier checkerboard example, in reality, all programs operate based on this hierarchical principle. An entity H is defined as a union of its sub-entities, which are its descendants, each potentially undergoing a transformation. This is represented by the formula you see here. H is the function of f under W of Z in gamma, which is defined as the union of transformations sub-entities. Gamma represents the set of subentities, and T denotes the post-transformation. This definition is applied recursively all the way down to leaf entities, those without any further subentities. A leaf entity simply returns itself, forming the base case of the recursion. To make this clearer, let's consider the colorful cube example. Imagine this colorful cube is constructed from several checkerboards of different colors. As you can see in the hierarchical example visual, the colorful cube is a union of these individual checkerboards, where each checkerboard might have a specific transformation applied to it. Furthermore, each individual checkerboard is, in turn, a union of smaller colored cubes, again, each with its own potential transformation. This hierarchical approach allows scene language to represent complex and diverse scenes in a consistent and unified manner. This slide shows an example of how the scene language, with its hierarchical structure, is actually implemented in Python code on the left, alongside a visualized hierarchy of a chessboard scene on the right. To realize the structure we've discussed, like the entity function and hierarchical composition in actual Python, the authors predefined a set of functions. These functions are essentially part of a domain-specific language tailored for scene generation. The process involves providing a language model with documentation for this DSL and an input prompt to the language model. The language model then utilizes its code generation capabilities to produce Python code that uses these predefined DSL functions to construct a scene. You can see a snippet of this generated Python code on the left, defining entities like chessboard, board, and chess pieces, and how they are composed. On the right, the diagram visualizes this hierarchy. The chessboard entity is composed of chess pieces and a board. The chess pieces entity is further broken down into individual pieces like pawns, rooks, and others, and the boards into squares. For more detailed information on the specific functions with these domain-specific languages used for implementation, the author refers readers to the appendix of their paper. Next, let's look at the rendering pipeline, which shows how the scene language translates into a visual output. As depicted in section A of the diagram, we start with the scene language, which is essentially Python code we've discussed. When this code is executed, it produces an output entity B. This output entity B is, as denoted on the slide, a combination of word, embedding, and post information for each component of the scene. Now, a key aspect of this framework is its flexibility with different graphics renderers. The crucial step here is the reparameterization function, as denoted as g_reparam c. This function adapts the output entity into a format suitable for a specific chosen graphic renderer. The nature of g_reparam, therefore, varies depending on which graphics renderer is used. Now, let's examine the actual rendering results, starting with text-prompted scene generation. In this set of experiments, the authors utilized an SDS-based model called MVDream as the renderer for their scene language framework. They compared their results against two baselines. MVDream used standalone, which read out scene language, and another state-of-art model, GraphDreamer. The evaluation is conducted using two types of prompts: numeric prompt, which explicitly specify the number of objects, and generic prompt, which the number of objects is not specified. Looking at the quantitative results in the table, for a numeric prompt, a particular impactful result is count metric. This measures whether the number of objects in the output matches the number specified in the prompt. The hours method achieves a perfect score of 1.0, indicating it accurately generates the specific number of objects every time. This is a significant improvement over the baselines. Furthermore, the alignment score, which is based on user study assessing how well the output matches the prompt, is substantially higher for hours compared to GraphDreamer and MVDream. The clip similarity score is also shown. The scene language method performs best. Visually, you can see example on the left. For instance, with the prompt an 8-layer shelf, the hours method generates a clear 8-layer shelf. Similarly, for 15 Coke cans stacking in a pyramid, it accurately produces the 50 cans as requested. Next is rendering results across various graphic renderers. The authors showcase this versatility with several examples. For SDS-based rendering, they used Gaussian splitting. For asset-based rendering, they employed a Minecraft-style renderer. For text-to-image generation, they utilized MIGC. And for graphics primitive-based render, they used Mitzvah. On the left, under text prompted, you can see examples like a detailed model of tennis court or interior scene of university-style hall. The scene language generates a representation that can then be rendered using both Gaussian splatting and Minecraft. Similarly, city skyline at sunset is rendered with Mitzvah and T2i, and marionette also with Mitzvah and T2i. Across these different renders, we observe that structurally similar and robust outputs are consistently produced from same underlying scene language representation. On the right, under image prompted, the scene language framework is compared with GraphDreamer. Finally, let's look at the experiments on scene editing with language instructions. A key differentiator for scene language compared to many other neural models is that scene editing is performed through the language model's code editing capabilities within the program space. As noted on the slide, because this editing happens at the code level, the scene language program itself, diverse types of edits can be applied without requiring separate modifications or retraining of the underlying models. This has significant implications. Many existing generative models struggle with specific, fine-grained edits. For example, an instruction like remove 2 blocks from the second top layer of the Zynga tower, and the tower should not be full, would be extremely challenging, if not impossible, for most conventional neural models to execute faithfully. However, scene language demonstrates a strong advantage in such scenarios. These examples illustrate that by operating on the explicit programmatic representation of the scene, scene language allows for complex compositional and precise edits that are often difficult to achieve with models that operate purely in implicit latent spaces. To summarize the key takeaway from this paper, first, the authors propose a powerful scene representation, which they call scene language, by effectively leveraging the code generation capabilities of language models. This is a shift from directly generating images to first generating a programmatic, structured description of the scene. Second, a significant strength of this representation is its versatility. It can be flexibly applied to a diverse range of renders, as we saw with examples like Gaussian splatting, Minecraft, Mitzvah, and T2i models. And it can also be integrated with existing neural models. This modularity demonstrates a novel and promising approach for generative models, allowing for greater control and adaptability. Finally, the authors suggest that this code-based approach is not limited to the examples shown but can be extended to handle even broader and more complex scenes. The inherent compositional nature of programs make this a promising avenue for further advancements in generating intricate 3D environments. This work effectively showcases how the symbolic reasoning and code generation strengths of language models can be harnessed to create rich and editable scene representation. That concludes my overview of the paper. Thank you for your attention.